Okay, welcome, Jordan, Ralph, and Bradley, and Jesus, and Victor, and Cesar. Thanks for coming. It's been a while, actually. We haven't met in a week, so hopefully you had a really good long break. So let me share my desktop and talk about what we're doing today. Okay, the plan, as always, I'll start out with a Q&A. So if you have any questions, I'll be happy to answer your questions. And then after that, we're going to get into a particular solution. So we have been pretty much focused primarily on homogeneous systems, because remember that if you have a homogeneous system, then you can write down the matrix, and then the null space of the matrix is the solution of the system. But sometimes you don't have a homogeneous solution. Sometimes you have a non-homogeneous solution, and you still want the solution. And that's where we're going to get into this particular solution idea. So after defining a particular solution, then we'll talk about a particular solution and how does that relate to the general solution. So you may have found one solution to the question, and you actually want to find out, well, what about all the solutions? How do you get all the rest of them? And again, if there's an infinite number of them, then you can't just list them all. So we'll talk about how you describe the entire set of solutions to a non-homogeneous system. Okay, and that will be, we have two sections actually, and I want to mention something. The particular solution is 5.9. And then we move to 7.1. So I'm skipping chapter 6, not because it's not important, but because you're supposed to already know chapter 6. And chapter 6 is about complex numbers. And hopefully you know what a complex number is. Do y'all know what one is?
Yeah.
Okay. You haven't done too much with them, but hopefully you do know. So we're not covering that chapter because that is actually kind of a prereq, stuff that you do in college algebra. And so just let you know that that's why we're jumping from 5.9 to 7.1, because it's stuff that you're supposed to already know. So 7.1, on the other hand, is new. And not only is it new, it's probably the most important applications most important applications come from 7.1. Today, we're going to do more of the theory, but then on Friday, we'll get into applications. So today, and I'll talk a little bit of applications, but today we're going to define what it means to be an eigenvalue and what it means to be an eigenvector of a matrix. Okay, very important. And then we'll talk about the spectrum of a matrix. You might have heard of the word spectrum before. Where have you heard that? Not in math.
Physics, the electromagnetic spectrum.
Yeah. So it comes up in the electromagnetic spectrum. And if you know a little about physics, and for example, hydrogen, does that cover all of the spectrum? What do you think? If you just have a hydrogen atom, does it emit all the spectrum, all colors of the spectrum and other waves, or just some? What do you think? Have you learned that?
I want to say all of them because you could also take into consideration radioactive decay.
Okay, so the answer is no. It doesn't do all of them, and which is really important actually, and I'll talk about that a little bit. So that's kind of, we'll talk, the book actually, that section doesn't do it, but it uses the word spectrum. So I figured I might as well use the word spectrum and talk about why and how that relates to physics. So then I'll talk about the characteristic polynomial for a matrix. And again, if you know what this is, then that's great, but you probably don't. And by the end of today, hopefully you'll understand it. It's not that hard, but it is really important. Then we'll get into the multiplicity of an eigenvalue. And then finally, I'll do an example or two where we actually find eigenvalues and find eigenvectors. So do some examples. So that's the plan for today. So let me start off. Do you have any questions? That could be about homework or something else. And I do want to let you know the answers to the back of the book aren't that great in this section. They're not all right. Any questions? Give you a moment to think about it, but hopefully you have questions because I'm here for you.
Could you go over problem 3 of 5.8?
Okay, so let me go find it. Unfortunately, I had it all set up as 5.7. So now I got to scroll. I get to pick one. Okay, 5.8, number 3. Okay, let's just a minute. I got to get it copied. Missed. One more try. Sorry. Almost there. Okay, so 5.8, number 3. All right, so what it says is let T go from R2 to R2, be a linear transformation defined by T of AB equals A plus B and A minus B. Consider two bases. B1 goes from V1, V2, or is V1, V2 equals 1, 0, negative 1, 1. And B2 is 1, 1, and 1, negative 1. So find the matrix M, B2, B1. So that means you're going from B1 to B2 of T with respect to the bases B1 and B2. All right, so what I like to do, again, it's a little different than the book's way because I find it a lot easier to understand, and that is draw a visual of what's going on. So what we have is we have B1. I'll just call that B1. Going to E. Come on. Going to B2. And then on the bottom, exactly the same thing. And we're going to have the transformation that goes from the top to the bottom. So let me do that. Sorry if it takes a moment. Do you remember this diagram that we had a week ago?
Yeah.
I never liked the annotation on this. All right, it's trying. Come on. Ah. Huh? It's not letting me. Just a minute. Let's try this way. Huh. Start again. Well, I might have to imagine it and see if it lets me do that. No, it's not letting me. Wonder what's wrong. Okay. So let me do it a different way.
I think you have the color on white.
Oh, maybe that's why. I didn't make it white. Format, try blue. That might be it. Thanks. See if that works. No, that didn't do it. Format blue. Let's try lines, see if it likes a line. Nope, doesn't like it. Okay, so I'll do a text. I apologize. I have no idea what's happening. I never liked this particular system, but it is what it is. All right, so let's go with text then. B1, E, B2. And then we're going to have an arrow and an arrow. So just pretend. Okay, and then E go into E, and they're going to there. Any questions so far? Okay, so now what we want to do is realize that if we're going to go from B1 to E, then to do that, it's just the matrix that looks like B1. Does that make sense? Is that clear?
Yeah.
Okay, so this first matrix from B1 to E will just be 1, 0, negative 1, 1. So let's do that. And I'm worried about that. I can make this work though. Okay, so what I'm going to have is a matrix in a moment. Huh? Do that. All right, so I'm going to have the matrix. Uh-oh. I don't know what Zoom's doing. Can you hear me still?
Yeah, I can still hear you.
Okay.
Yeah.
Something's going
I
wrong
can't
with
see the
Zoom.
screen.
Yeah, the screen just lost it. I have no idea what happened. I didn't do it. Maybe I did, but I didn't know it. Okay, but I definitely lost my annotation. Sorry about that. So, but my matrix going from B1 to E is going to be one, 0, negative 1, and 1. 1. Any questions on that? And in fact, let's do the following. Since I'm here again. B1, E, B2, and we'll have an arrow. We'll pretend it's an arrow. Okay, that's as good as we'll get. So there's a matrix from B1 to E. So what I'm going to do is I need to get from B1 to B2 on the bottom, because going from top to bottom is a linear transformation. Going from right to left is a change of basis. Is that clear?
Yeah.
Okay, so I just did B1 to E. Now I need to go E to E using our transformation T. So to do that, to find the matrix of T from E to E, I say, where does it take 1, 0? And it takes 1, 0 to 1, 1. And that'll be my first column. And I say, where does it take 0, 1? And that gets sent to 1, -1. And that'll be my second column. Have I lost you?
No.
Okay. Then what I need to do since I've now gone from B1 to E on the bottom, now I need to go to B2. So the B2 matrix, to go from B2 to E, would be 1, 1, 1, -1. Is that clear? So that's just a note. So I'm going to type that in even though it's not right. So 1, 1, 1, -1. What's wrong with that?
You need the inverse.
Yeah, we're not going from B2 to E. We're going from E to B2. So that needs to be inverse. You following that?
Yes.
Okay. So that's going to be our matrix. Do you need me to work this out by hand or by symbol lab? Like
No.
how to multiply the matrices and how to find the inverse?
No.
Okay. It's not that hard. It's just 2 by 2s. I wouldn't even use symbol lab on this because 2 by 2 is easy, especially if you have a piece of paper. Typing is a lot harder. So does that totally make sense?
Absolutely. Thank you.
Yeah. I mean, I could do it the book's way, which is without using any diagrams, but I find it really hard to follow what's going on. For me, I see I'm starting at B1, I go to E, then I go down to E using a transformation, and then I go to B2. And I learn how to make those matrices. And that's it. Okay, other questions? Other questions? If they're not, then I can go on and talk about new material. Okay, if there's no questions, let's move on. Okay, so here's a big definition. And it's the following. Let T be a linear transformation and B be a vector. Okay, now do you guys remember what a linear transformation is? It's been a week, so I can't assume anything anymore. Do y'all understand? Do you remember what a linear transformation is?
It's the transformation of a matrix that just has one output to every input.
It can be, but actually, in general, it doesn't have to be a matrix. So it's a function such that T of x plus y equals T of x plus T of y, and T of Cx equals C times T of x. So it means that it's linear. So you can split up pluses and you can pull out constants. Okay. And then we had a theorem that all linear transformation from Rn to Rm can be written as a matrix. Okay. Later on, we're going to find out there's linear transformations that aren't from Rn to Rm. But from now, that's why you jumped into the matrix, because for now you can get away with that pretty well. But that's going to change. Instead, you want to remember T of U plus V equals T of U plus T of V. And T of K times U is K times T of U. Okay. And then if V is a solution to Tx equals B. So that means if I plug in V, it works. Then V is called a particular solution to the equation. Any questions on this idea?
Is x just a variable?
Yeah, x is a variable, which is a vector, right?
Okay.
Yeah, x is a variable, it's just a vector. Since it's t is a linear transformation, it's given that there's a domain. Okay, any questions on that? Okay, so here's an example. Okay, so let's suppose that t of x equals b, where t is defined by t of x equals a times x. So good old-fashioned matrix linear transformation. And let's suppose A is this matrix, 0, 1, 0, 0, 0, 2, red as rose. And B is the vector 2, 6. Which of the following is a particular solution? I think I'm going to do this so you can actually see the definition. Okay, we have 5, 2, 3, 5, 2, 1, negative 4, 2, 3. I want to see if you can come up with the answer. There might be one of them works, might be two of them work, might be none of them work, maybe all of them are particular solutions. You have to tell me. So again, good thing in the chat box, you can let me know. And if you want to call them, I don't know, A, B, C if you want, in order. Let's see if you can work this out. I'm going to give you a minute or two. It doesn't take long. So let's see how you do. And again, you definitely need that definition.
So what I just did was I multiplied A and our potential solutions, and only one of them got the same as B.
Okay, do I have a second on that?
Or two of them are actually.
All right, do I have a second on that? And you're not allowed to second yourself, by the way.
Yeah, A and C works.
Okay, good. So we have a second and a third, actually. So A and C. So we notice that 5, 2, 3 works. Negative 4, 2, 3 works, but 5, 2, 1 does not work. Okay. Does anyone need me to actually write it out? Or were you able to do that, all of you, by hand? Because I'm happy to write it out if you need it. Anyone need that? Okay, so notice that this particular equation, Tx equals B, has more than one particular solution. Okay. Do you think it has only two?
No.
No. How many do you think it has? We did this in the first week of class.
Infinite.
Yeah, it has an infinite number of solutions. Okay, has an infinite number of solutions. And that was a theorem we had. Whenever you had a non-homogeneous equation, then if you have more than one solution, you have an infinite number. You can't just have exactly two. In fact, you can't even have just one. If you have a solution, you have an infinite. Okay, as long as B is non-zero. And if B is zero, if you have more than one, you have an infinite. Okay, so there are an infinite number of solutions. And here, the first and the third on this list are solutions. The second's not a particular solution. So you call this a particular solution. All right. Anyone recognize what this particular thing is doing from a past class? I don't expect you to recognize it, but who knows? Maybe one of you will see it. You don't see it? Okay, I'm going to tell you, and you're going to you're not going to say, oh, I should have seen that, because you wouldn't have. A is the derivative. Did you all see that? You still don't see it, right?
Nope.
No, and it's a derivative of a quadratic polynomial. Okay, and because if you have a plus bx plus cx squared, and you let ABC be the vector, then a times the ABC will actually be the linear coefficient of the derivative. Do you believe me?
Yeah, I'll take your word for it.
Okay. So notice this first one is 5 plus 2x plus 3x squared. And if I take a derivative of 5 plus 2x plus 3x squared, I get 2 plus 6x. And there's my 2 and 6. See how that works? Whereas the second one was 5 plus 2x plus x squared. And if I take its derivative, I get 2 plus 2x. And that's not 2 plus 6x squared, 6x. And that didn't work. Whereas negative 4 plus 2x plus 3x squared, its derivative is 2 plus 6x. Okay, so it's deep. That's what I'm trying to say. It's not just a matrix. Turns out all of calculus can be done this way. Okay, it's a weird way of thinking about it because you've probably never thought about calculus this way, have you?
No.
No, but this is calculus. Okay, and again, I didn't expect anyone to come up with the idea that the example above is a differential equation because it doesn't feel like one, but it is. Any questions on that? Okay, and we'll be doing that in a deeper way later in this class. But right now, I just wanted to kind of show you, give you the idea, and we'll formalize it in a few weeks. All right, here comes a big theorem, a major one. And this comes up in a huge way next quarter. What class is next quarter?
Differential equation.
Yeah, differential equations. And that's why I wanted to show you the example above, because this is a big deal for next quarter. And it says the following. If V is a solution to Tx plus equals B, so that means V is a particular solution to this equation, and W is in the kernel of T. Do y'all remember what kernel meant?
It's the domain of the linear transformation.
No.
Also null space.
Null space, yeah. So as a matrix, it's the null space. Okay. In kind of algebra, you call it the roots or the solution, right? Where it's 0, set it equal to 0 and solve. Okay, and that's the kernel. So W is in the kernel of this linear transformation. Then every particular solution can be written as V plus W with W in W. Any questions on what this theorem says before I go and prove it? Any questions? Okay, let's prove this. It's not that hard to prove, and it's important. And if I don't prove anything, then it's not fair because I make you prove things. Sound reasonable? So I better prove some of these theorems. So let's do a proof. Okay, so we basically start with what's given. Let V be a solution. And what does it mean for V to be a solution? Very obvious.
T of B equals B.
Yeah, TV equals B. That's what it means to be a solution. It means if I plug it in, it works. And what does it mean for W for little w to be in capital W?
Wouldn't big W be a basis?
But W is a space, not the basis. So
So-
basis is not part of this, actually.
W is a subspace of big W.
Okay, so W is in capital W. Capital W is the kernel of T. What does it mean for little w to be in the kernel of T?
There is a solution also.
That's what it means to have a kernel. But what does it mean to be in the kernel? I know it's been a week. Do you remember? It means that TW equals 0. Because kernel means that if you plug in, you get 0. Do you remember that? Anyone lost on that? Because again, none of you jumped into the answer. It's very simple, but you have to understand it. So kernel means that if you apply T to it, you get 0. Any questions on that? Okay, so then how about U be a particular solution to Tx equals B? What does that mean? It's very simple. What does it mean to be a particular solution?
That T of U equals B.
Yeah, TU equals B. Because that's what particular solution means. It means if you plug in, you get B. Whereas a homogeneous means if you plug in, you get 0. So you got to get those words down. The vocabulary is sometimes the hardest part. So we need to show that U can be written as V plus W. Any questions on that? That's our goal, because it says every particular solution can be written as V plus W for some W and W. So here's what we do, and this is the trick. What do we know about T of U plus V? What's that equal to?
T of U plus T of B.
Yeah, so that is equal to T of U plus T of V, because T is a linear transformation, means you can split pluses. Any questions on that idea? What's T of U?
B.
B.
Oh, sorry, I don't want T of U plus B. Sorry about that. That doesn't help. T of U minus. And I can split minuses too. Do you remember that? So T of U is B. What's T of V?
B as well.
Uh-huh. Now here's the easiest question in the world. What's B minus B?
0.
Good. Told you it was the easiest in the world, wasn't it? All right. So what do you know about U minus V? In words.
Shouldn't they be the same?
U minus B should be 0.
Yeah, take a look. Do they have to be the same? No. 523 is not the same as negative 423. Right? Do you agree?
Yeah.
Yeah. So they don't necessarily have to be the same, but we know U minus V is in the kernel of T. Because that's what it means. If I apply T to it, I get 0. Is that clear?
Yeah.
And the kernel of T was equal to capital W. So U minus V is equal to little w, where little w is in capital W. Have I lost anyone yet? All right. What's the last step? Read the theorem, see what our goal is. We want to write V, we want to write U as a v plus w. Can we do that?
Yeah, we just
What do we have
move
to do? Hmm?
we just move b to the other side.
Yeah, we just add v to both sides. And u is equal to v plus w. Oops, plus w. And that's it. That's the theorem. That's the proof. Did I lose you? It's easy to watch, isn't it? But coming up with the proof is not as easy. In fact, I even had a plus instead of a minus at the beginning. And it's like, oh yeah, I want it to be minus because I need to get 0 when I'm done. So I changed it. Any questions at all on this proof? Okay, why is that really important? Why is this
Now
a
we
really
can
important
check to
theorem?
see if we're correct with our particular solution.
Well, you might be able to check to see if you're correct, but it's actually more, there's a real reason why it's important, not just for checking.
Linear combinations.
Combinations, not quite. All right, let me let you know. Okay, so here's the reason. Because I can write down steps to solve tx equals b. So step 1 is solve tx equals 0. And we spent a lot of time finding that because if we know our t, we can write down, you can usually write down the matrix for t, and then you're finding the null space for the matrix for t. Usually a basis of that. Is that clear? Step 2 is find a particular solution. Okay. And in fact, let me write in step 1, solve for t of x equals 0 means find a basis for the null space. Okay, or kernel, whatever you want to call it. Maybe I'll call it kernel because linear transformation, same idea. Step 2 is find a particular solution. Okay, and the nice thing is any particular solution will work. Whatever's easy. Is that clear? Okay, and again, maybe we'll call that V just to make life easier. And let's say the basis for the null space is, let's call it W1 through WK. And then step 3 is the solution R. Well, you start with your V. Let's write it as an equation. V plus C1, V1, W1, sorry, plus C2, W2, plus dot dot dot, plus CK, WK. Any questions on these steps to solve Tx equals B? Okay, otherwise we don't really have a way of doing it so easily. Okay, and in the real world, often you know a particular solution because you actually did an experiment and you watched it happen. So that's one of the solutions. Does that make sense? So you have your model for what you're doing. So you do one experiment and you find out what that experiment did, call that the V, then you do the null space, and then you've got your all possible solutions. Any questions on this? Okay, so particular solutions are pretty important. All right, so let's do an example. And I think I'm gonna, since I did step by step, hopefully that's enough that you can actually try it without me just showing it to you, and then we'll do it also. There we go. All right, so the question is, find a general solution to the matrix, read rows 1, 0, 1, 2, 0, negative 1, 2, 1, 2, negative 1, 4, 5 times vector x equals 3, negative 2, 4, given that 1, 3, 0, 1 is a solution. I'm going to give you a couple minutes to try this out. We have some time. It'll take you a few minutes. And do it with the steps. And the hint, step 2 is the easiest of all in this case. So let me give you some time. I'll be quiet. But if you're stuck, you can always, ask or pop in the chat box. And I actually made this one really easy to do by hand. And when you have the solution, maybe you can put it in the chat box. Or at least say you have the solution, so I know it's time.
Is C just a scalar?
The C1, C2, those you mean?
Yeah.
Yeah, those are scalars. Yeah,
Okay.
in this class, if I ever use A, B's, or C's, those are scalars, and U, V's, and W's are always vectors. So that's just kind of the notation, the standard notation. And capital A, capital B, capital C would be matrices.
So we have a basis for the null space, and we have B. The solution will be B plus C1, and the first uh, vector of the basis plus C2, and the second, right?
Exactly. Did you get it?
Yeah.
Anyone else get it? All right, give another minute or two. Sorry, Victor, but I want at least 2 people to have it before I go over it. You know, and unlike face-to-face class, I can't look and see if you know, where you are. All I see is a name on the screen. So you have to let me know. And if you're stuck, let me know and I'll help you get unstuck. Hopefully you're getting through it. I tried to make the numbers all nice when I chose this or created this. Any questions? And the answer is not completely unique. So again, if you got something different, then that's possible that you could both be right. Okay, we got a second answer. All right, I think I'm going to do this one because I think it's worth it. Let me put it on its page so I can work it out. All right, so the first step is to find the null space. So how do I find the null space? What's the first step in finding the null space?
RREFT.
Yeah, we're going to RREF it. And I'm not sure if you're like me, then you did this in your head. Did you do it in your head? Because I noticed that if I take the first row, multiply by 2, and add it to the second row, I get the third row, which means the third row zeroes out. Because it's if it can be written as a linear combination of the others, then that means it'll become a 0 row. And I guess I should write RREF so you know what I'm doing. RREF. I'm going to call it A. Whoops, A for the matrix A, that corresponds to the T transformation. And then I'm going to multiply the second row by -1. I mean, I could use Symbolab too, but this was faster actually. Any questions so far? Okay, once we've RREF'd it, then what do we do?
We can write the equations.
Yeah, I can write equations. I like to identify the free variables in the pivot columns. And notice that the first 2 columns are pivot columns, and the last 2 are free variables. Is that clear? So that means that if I think of this as an equation, and I let the first free variable be 1, and the second free variable be 0, then my first component is going to say that that component plus 1 equals 0, or that component must be -1. Second, that component plus -2 is 0, so the second component will be 2. And then we let the first free variable be 1 and the second be 0. I guess I need to go curly brackets because we got a basis. And maybe I'll go null or kernel of T is spanned by that first vector. And then we do the same idea, but now I'm going to let the second free variable be 1 and the first be 0. So then we get 1 plus 2 equals 0, and we get -2 for the first. And for the second, we get 1 minus 1, or we get this variable -1 equals 0, and that means that we get 1. And then we let the first free variable be 0 and the second be 1. Anyone lost on getting the kernel? Okay, second step is basically given for us. 1, 3, 0, -1. There's our vector. So that means that the solution is the following. Well, we just take our vector v, which is 1, 3, 0, 1, plus, I guess I need to make it equation. C1 times -1, 2, 1, 0. And then plus C2 times -2, 1, 0, 1. And there's our solution. By the way, how many solutions do we get?
Infinite.
Yeah, we get an infinite number of solutions. Now, and this is a little weird. In linear algebra, that's not good enough. Okay. It's not good enough because how infinite do we have? And we actually have two dimensions of infinity because we have a C1 and a C2. Okay, it's not a subspace, it turns out. So the set of solutions is not a subspace of R4. In particular, 0 is not in it. Do you agree? The 0 vector is not in this because if you take that matrix, you multiply by the 0 vector, you don't get 3, negative 2, 4. So note that the solution space, or let's just say solution to a non-homogeneous equation is not a subspace. Okay, any questions on that? Because if it's not homogeneous, 0 is not in it, and subspaces have to have 0. Any questions on this example? Any questions? Okay. It's hard for me to explain why you care about this. You really care about this for next quarter, and that is next quarter when you do differential equations, you're going to have non-homogeneous differential equations, and you're going to solve them with matrices, and this is how you're going to do it. That's all I can tell you. I can't say much more than that. But do you believe me? Hopefully you do. Okay, so let's move on and let's jump a chapter. So this is like a key definition, especially if you're looking at applications of linear algebra. This is really important. So here it is. Let A be a matrix and V be a non-zero vector. And who knows how to read this letter?
It's a gamma.
Good try. It's not a gamma.
Lambda.
Lambda. Okay, lambda is a real number. Okay, where have you seen lambda in physics before?
Frequency.
Frequency, right? Wavelength, actually, usually wavelength. And frequency, it could be frequency. So you see it as frequency in kind of frequency wavelength stuff. Okay, and there's a reason, and that's because it comes from, which will not be obvious at all today, but you got to trust me. Let V, then V is an eigenvector, very important word, eigenvector, of A with eigenvalue lambda if A times V equals lambda V. It's a very simple definition. So we look at the equation AV equals lambda V, and if it works, then V is an eigenvector, and lambda is its eigenvalue. Sometimes we'll say the corresponding eigenvalue. Okay, the set of all eigenvalues of A is called the spectrum of A. Okay, and then note A must be a square matrix. Why must A be square?
To have an inverse.
No, it doesn't have to have an inverse, actually. A does not have to have an inverse. But why must it be square for this definition to even make any sense? Anyone know? So I'll let you look at it.
I'm thinking something to do with the determinant.
No, nothing to do with the determinant, but good try. No, it's all here. You don't actually have to say anything other than read something from this definition. You don't see it? Okay, we have AV equals lambda V. All right. If A is not square, then AV can never be a multiple of V because AV would be a different dimension than V. Because non-square matrices change dimension of vectors, right? So if you have, say, a 3x4 matrix, and you put in a 4 vector, you get a 3 vector out. Do you remember that? So even to say AV equals lambda V, A has to be square, or it just, it can't ever happen. Does that make sense? Maybe I'll even scroll up and I'll give you a kind of what I'm talking about. So here we had a 3x4 matrix, and X was a 4-dimensional vector, right? We could plug in this V and it works. But when you multiply, you get a 3-dimensional vector out. Do y'all see that happening? So if it's not square, you don't get the same, you change dimensions. And this says AV is lambda V, and that means our dimensions didn't change. Multiplying by a constant doesn't change dimensions. So that is a big deal. So it's only looked at for square matrices. As I mentioned, you've heard of spectrum in physics, right? And to explain it is hard, but I'll say it. And this is one of those, just trust me. If you look at Schrodinger's equation, basically, and that kind of stuff, then, and if you look at it using quantum physics, then it's a matrix equation. And it turns out that the wavelength that you get are going to be, all the possible wavelengths that you can get are going to be the lambdas. And this is one that it's not my job to explain all the details of why. But if you take an advanced physics class, you'll learn about it. So that's why they call it the spectrum, because it kind of refers to the same idea. This is like the spectrum for a hydrogen. I don't know if you realize, but when we look up, like to look for exoplanets, and we try and figure out what they're made out of, this is what we're doing. What we're doing is we're detecting the wavelengths, the spectrum that comes when we look at it. And it's a fixed finite number of things that we see. And then we go backwards and say, what matrix could that be that makes that happen? And then we can say, well, what element or molecule has that matrix? And then we can identify the molecule. And if you have no idea why that's the case or what I said, that's okay. You're not responsible for it today. But if you take advanced physics, then you need to learn this stuff. Sound fair? Kind of cool stuff, isn't it?
Yeah, that's cool.
Yeah. So whenever you hear about spectral analysis, that's what it means. It means finding these lambdas. Okay. Is that you can take a picture, it gives you the lambdas, and then you undo it and say what element has the matrix that gives you that lambda. And then you can do that. And it even gets a little more advanced, because if it's far away, it's moving. And if it's moving, then that means that the spectrum changes because of the Doppler effect. And it's really cool. So I'm not going to get into its very advanced physics, but it's beautiful advanced physics, I'll tell you that. Any questions on the idea of what an eigenvalue and eigenvector are? So again, one example is looking at molecules and figuring out what they're made out of. But there's lots and lots and lots of other examples besides that. Okay, AI uses it in a big way, I'll tell you. But again, too hard to explain. So one of the problems with this class, by the way, is that most of the applications are too hard. You have to have advanced physics or advanced engineering to be able to understand the application. So that's why you don't see quite as many applications in this class. But when I talk to former students that graduated with engineering or physics, and I ask them, you know, what was your most important class in terms of using it? Most of them say linear algebra. So this one, trust me, or trust them. Sound good? Okay, so now comes a major theorem. Because this is all beautiful. AV equals lambda V. But if we have a matrix, we want to be able to find A, V, and we want to find lambda. You know, what are the eigenvalues and what are the eigenvectors? And the next theorem is what allows us to do it. And here's the theorem. So V is an eigenvalue of A. V is a eigenvalue of A. This should say eigenvector with eigenvector lambda if and only if V is in the null space of A minus lambda I. So the good news is we know how to find a null space. Do you all agree? By the way, what is I? When I say I, what do I always mean? That letter?
Identity.
That's the identity matrix. And remember, A is a square matrix. So you take the identity of the same dimensions. Any questions on that? And if you multiply that by lambda, by the way, that is the matrix that's zeros everywhere except the diagonal. And in the diagonal, it's all lambdas. Any questions on this idea? All right. Well, how do we prove it? Any thoughts? Oh, maybe I shouldn't have done what I just did, because you need to see it. How do we prove it? Any thoughts of what we need to do?
We need to prove that d of a minus lambda I equals 0.
Yeah, we don't really have a t here. A is the linear transformation in this case. Okay, so maybe I'll start you off. Well, we have to say, let's suppose we have an eigenvalue, v with eigenvector lambda. So what does that mean? So if v is an eigenvalue, oh, you know what? I have this backwards. So v is the eigenvector. V is a vector, and lambda is a value. Sorry about that. So if E is an eigenvector with eigenvalue lambda, then by definition, what does that mean?
AV equals lambda V.
Yep, that's the definition. So I can write that down. So let's do it. So AV equals lambda V. There's lambda. All right, well, the good news is now I just play with it. So what I can do is I can subtract. Let me ask you, can I do this? Can I say just subtract lambda V from both sides and do the following? So let's copy this guy. So am I allowed to say AV minus lambda V equals 0? Can I say that? What do you think?
Yes.
Yeah, that one looks okay. Can I do the following? Can I factor out AV? And get A minus lambda equals 0. Can I do that?
Yes.
One more guess.
No.
No, you can't do that. What's wrong with that?
I mean, wouldn't that be considered dividing a vector?
No, I didn't do any dividing. Let me show you what's wrong with it. Let me give you an example. I think the easiest way. What if we had how about 2, 1, 3? I'm just throwing in a matrix. Sound good? 5. Lambda's a number, so minus, how about 7? V equals 0. What's wrong with even saying this?
That would imply that the matrix or lambda is 0.
No,
Or
there's
V.
something wrong. There's just something wrong. Very wrong. All right, tell you what. You tell me what 2, 1, 3, 5 minus 7 is.
Nothing.
Nothing. You can't do it. Do you agree? You can't take a matrix and subtract a number. Do you agree? Do y'all agree with that?
Yeah.
This is wrong. So you can't do this. So this thus is wrong. But here's what I can do. I can go to where I was and say AV. See if it lets me. No, it doesn't. That's okay. AV minus lambda times IV equals 0. Do you agree that V and IV are the same thing?
Yeah.
That's what the identity does, right? Okay, so we know that AV minus lambda I times V is equal to 0. That we can do. And next, now I can factor out the V. And you can say A minus lambda I times V equals 0. And now it makes sense because A minus lambda I can do that subtraction. That's subtracting 2 matrices. Any questions on that subtle step? Why am I done?
Because B is a multiple of A minus lambda I, which is in the null space.
V is not a multiple of A minus lambda I. A minus lambda I is a matrix, V is a vector.
Oh, because A minus lambda I equals 0 and B times 0 equals 0.
No, you can't do that. That's not true. Be very careful about using rules of algebra. Rules of algebra don't work with matrices. If you have two things multiplied equals 0, it does not mean one of them is 0. The key is you have to look what our goal is. I think you got lost track of the goal. We need to show V is in the null space of A minus lambda I. What does it mean to be in the null space of a matrix? Hopefully you remember that. A minus lambda I is just a matrix. You can think of it as like B. B times V equals 0. And what does it mean to be in the null space? Do you remember? A vector is in the null space of a matrix if the matrix times the vector equals 0. So we're done by definition. That's just what it means to be in the null space. Hence, V is in the null space of A minus lambda I. By definition, that's just what null space means. Anyone lost on that? Okay. So next comes an example. Let's do an example. Find the eigenvalues and eigenvectors of A equals 1, 3, -2, -6. Any questions on the question? So what do? What's the first thing we have to do? Using the big theorem.
Find a non-zero vector.
That's the last thing we have to do.
Find lambda.
Okay, that's the second thing we have to do. The first thing we have to do is write down what A minus lambda I is. So we start by writing A minus lambda I. Okay, well, that's equal to this matrix, 1, 3, -2, -6. Minus lambda times I. And I is 1, 0, 1, 0. Ah, 1, 0, 0, 1, sorry. Anyone lost there? Okay, that I can actually do the arithmetic. And in fact, maybe I'll do it slowly because it seems like you might need it. It's been a while. The 1 week is tough. So I can multiply the lambda through, and I get lambda 0. Zero lambda. Any questions on that? Now that is equal to, well, let's just do the subtraction. So that's going to be 1 minus lambda, 3, -2, negative 6 minus lambda. Any questions on that? Just want to make sure anyone lost on what this matrix arithmetic. Okay, so I just found a minus lambda I. What do I want?
When lambda.
What am I looking for? So I'm looking for the eigenvectors. And the eigenvectors are what? Once I get a minus lambda I, they are the big theorem said.
Yeah,
They're in the null space.
Right, in the null space of this matrix. Okay, well, the first thing is when, and it needs to be non-zero because eigenvectors can't be zero. When does a 2 by 2 matrix or any matrix have a non-trivial null space? Here's a hint, TFAE.
The determinant is not 0.
Right. Actually, it's the opposite. When the determinant is 0. It has a trivial null space when the determinant is not 0. I mean, it is not 0. It has a non-trivial when the determinant is 0. Any questions on that?
Okay, so non-trivial when the determinant is 0, but then trivial when the determinant is 0, or
So it's the other way around. Other way around. So it's the null space. If the null space is trivial, then the determinant is non-zero. If the null space is non-trivial, then the determinant equals 0. So we could set the determinant of this matrix equals 0 to find out which lambdas will give you an eigenvector that we've got. Okay, well now the good news is this is a 2 by 2 matrix. 2 by 2 matrices have nice determinants. Do you remember? You don't have to do any kind of adjoint operation or anything like that. Do you remember it's AD minus BC? Do you remember that little formula?
Yeah.
So I can write AD, which is 1 minus lambda, times negative 6 minus lambda, and then minus BC, which is 3 times negative 2. And I set that equal to 0. Anyone lost on what I just did? Okay, now that I have that, then I just continue on. And the good news is now it's basic algebra. Intermediate algebra, I should say. It's not beginning, it's intermediate algebra. So a FOIL. And I get lambda squared. And then we have, let's see how many lambdas we got. We got a 6. And then minus 1 is 5 lambda. And then we're going to have a minus 6. Just doing basic algebra, basic intermediate algebra. And then plus 6 equals 0. Any questions on that so far? Okay, next we can just basically simplify this. And the minus 6 plus 6 goes away. And you get lambda squared plus 5 lambda equals 0. I'm hoping you're like relaxed now because it's actually math that you can all like do without hardly thinking. Do you agree? Other than the fact that it's a Greek letter. I do want to mention something. This 5 here is negative the trace of this original matrix. And the trace is the sum of the diagonals. 1 plus -6 is -5. Take negative that, and you get this 5. And it turns out the determinant is equal to 0, and this -6 plus 6 is the determinant. And that's not a coincidence. It always works that way. So it turns out that when you work this out, you're always going to get lambda squared minus the trace of lambda plus the determinant of the trace of a plus the determinant is equal to 0. Trace of a times lambda plus the determinant equals 0. Okay, I'm hoping you can all solve this. What's lambda?
0 and -5.
Good, good. That was supposed to be intermediate algebra, which you should all be able to do. Maybe even beginning algebra at this point. So what we can say now is lambda equals 0 or -5. Any questions so far? Okay, so I have now found the eigenvalues for this matrix. Any questions on that? Now, for each eigenvalue, then we could look for eigenvectors. How do you think we can find eigenvectors? Any thoughts?
Is it maybe a vector composed of the eigenvalues A or?
No, not quite. Good try, though. This is going to sound really easy, and it is. We plug in. If we plug in lambda equals 0, we get a matrix. And if I plug in lambda equals 0, I get 1. And then 3. Do you agree? 1 minus 0 is 1. And then 3 is 3. And now I'm going to give you a trick. I don't want the matrix. I want the null space of the matrix. Is that clear? Because that was a theorem, is that the eigenvectors will be the null space of the A minus lambda I. Well, I already know the determinant is 0. If the determinant is 0, then the second row here must be a linear combination of the first, and when you RREF, you're going to get 0 and 0. And you can always do that, it turns out, if you have a 2 by 2. And I want the null space of this. What's the basis for the null space?
One, 0.
Not quite. Wait, 1, 0. No, that doesn't work. If I multiply this matrix by 1, 0, I get 1. I don't get 0. I get 1, 0. I don't get 0, 0. You see? -3, 1. How did I get that? Anyone see it? If I write down the equation, that's like x plus 3y equals 0. So x equals -3y. So let y be 1, and then x is -3. Have I lost you? So finding the null space is really important in this class. You got to be able to do that. So that means that we have the following, and that is that the vector -3, 1 is the eigenvector corresponding to the eigenvalue lambda equals 0. Anyone lost on this arithmetic, on this algebra that I've done? Okay, well, how do I get, okay, and I should say not the, but a. It turns out any multiple of this will be an eigenvector. And I'll let you see that that's true, because that's how null space works, is that once you have a vector, any multiple of that vector will be in the space, and the null space was a subspace. Okay, so a basis would be -3, 1 would be a basis. Okay, now let's get the second one, and that's for lambda equals -5. So I'm going to just literally copy and paste and change what I need to change. So now if lambda equals -5, then 1 minus -5 is 6. And then 3. And then when you RREF, you get 0 and 0 again. If you want to plug in -2 and -6 minus -5, which would be 1, you'll realize RREFing gives this. Okay, and then if we want to find the null space of this vector, well, I could let y be 2, and then x would be -1. And do you all see that if you multiply 6300 by -1, 2, you get the 0 vector? So that means -1, 2 is an eigenvector corresponding to the eigenvalue lambda equals -5.
I have a couple questions. First,
Sure.
What was your justification again for having the row of zeros?
Okay, the justification is if the determinant is 0,
Mm-hmm.
that means that if you RREF the matrix, you'll get a row of zeros on the bottom.
Got it.
So that means I just skip the step and say I get a row of zeros on the bottom by theorem.
Mm-hmm.
Okay, and if you want to do it, you will get it. But it's a lot easier to say, hey, by theorem, it's a row of zeros on the bottom.
Okay.
And that works for 2 by 2. You do get a row of zeros on the bottom for 3 by 3, and that's fine, but you got to double check that the first 2 rows aren't multiples of each other.
Mm.
And then you can put a row of zeros on the bottom, and that always works.
Okay. And then my second question is, what does an eigenvector represent geometrically speaking?
Very good question. All right, so here's what it represents. If you look at, and again, we're gonna have a whole section on this, by the way. But if you look at the matrix, I'm going to go in 2 dimensions. It's easier to think about geometrically. If you look at the matrix and you apply that matrix times the eigenvector, you get a multiple of the eigenvector, right? By definition, right?
Yeah.
And if you apply it again, you still get a multiple, right? So if you look at the line that the vector sits in, then applying the matrix keeps that line fixed.
Okay.
Okay. So it turns out we have 2 eigenvectors. We have -3, 1 and -1, 2. Right? So the 2 lines that these vectors give, because the vector always sits on a line through the origin, are fixed by multiplication of this matrix. Do you believe that?
Yeah.
All right. So it turns out, and we'll prove this not today, it turns out that the eigenvectors are linearly independent that you get going this way. And in this case, form a basis for R2. Do you believe that? There's two of them.
Yeah. Mm-hmm.
Well, it turns out that using that basis as your coordinates, if A is your key transformation, is the best basis there is. And you have to trust me on that. Because what happens is the X and Y axes won't change
Okay.
by multiplying by this matrix. Is that clear?
Yeah.
Yeah, so that's geometrically what's going on with 2 by 2. 3 by 3, same idea, but now you're talking in 3 dimensions. As soon as you move to 4 by 4, it's hard to talk geometry. Do you agree?
Yeah.
Yeah, we don't have a good language for 4-dimensional space, but you can do it. All right, so now let's state a corollary. And the first is the spectrum of A is a set of all lambda such that the determinant of A minus lambda equals 0. Do you agree that that's kind of how what we just did? Is if we wanted to find the eigenvalues, we took the determinant of A minus lambda I, set it equals 0, and that gave us our eigenvalues. Any questions on that? Okay. So again, there's nothing really to prove there. It's just proof by TFE. Okay, definition. And this is important. So if you take the determinant of A minus lambda I, notice I did that in my example. I took the determinant of A minus lambda I, and I got lambda squared plus 5 lambda. And you see I got a polynomial. Okay, and by the way, this was a quadratic. If we had a 3 by 3 matrix, what kind of polynomial do you think you get?
A third degree.
Mm-hmm. You get a 3rd degree polynomial. And a 4 by 4 will give you a 4th degree polynomial. Is that clear? So this polynomial that you get is called the characteristic polynomial of A. Any questions on that? Okay, now you get a polynomial and you have these roots lambda, and you know from algebra that sometimes roots can have multiplicity. So you might have, say, lambda minus 1 quantity squared times lambda plus 2. So the multiplicity of 1 will be 2 because there's a quantity squared. So the multiplicity of lambda for the characteristic polynomial is called the multiplicity of the eigenvalue. Any questions on that? Okay, very important, by the way. Okay. Okay, and by the way, I'll give you a little, again, I'm not going to prove anything. This is like, trust me on this. But you learn about in chemistry, and if you have a hydrogen atom, for example, keep it simple, then the electron, did you learn about electron states? Did you learn about p shells and s shells?
Yeah, the orbitals.
Mm-hmm. Do you know what those are?
A region of space in where an electron might reside.
Right. And do you know why there's only a fixed number of them instead of anywhere?
No.
Because of this. because there's a fixed number of possible eigenvalues in the Schrodinger equation for hydrogen atom. And if you look at the eigenvalues for the Schrodinger equation for the hydrogen atom, then that'll give you the orbitals. Cool stuff. And again, I can't go into details because way too advanced. But you can trust me that when you learn about orbitals, those orbitals are found by looking at the corresponding matrix and looking at the eigenvalues. So they're big, big, big applications, but hard applications. Okay, find the characteristic polynomial, the spectrum and the multiplicity of each eigenvalue. We only have a few minutes, but that's enough because I gave you a really easy one. So what do we have to do?
A minus lambda I.
Yeah, and I did the other one in step by step, but now I'm just going to do it. So it's going to be a 2 minus lambda. Got to get to the lambda. 3 minus lambda. And 2 minus lambda. And then I want to take the determinant of that matrix. Any questions so far? Why is this a really easy determinant?
It's an upper triangle matrix.
Yeah, it's triangular. When you have a triangular matrix, you can multiply diagonals. So the determinant is just going to be 2 minus lambda. They always make it hard to get lambdas. There we go. 2 minus lambda times 3 minus lambda times 2 minus lambda. That's your determinant. Do you agree? So that is the characteristic polynomial. If you feel like multiplying it out, you can, but you don't have to. Any questions so far? So maybe I'll even write.
So that right there is the characteristic polynomial.
Yep. I'm getting there. I just gotta make it happen. Is the characteristic polynomial. Of A. Okay. And by the way, sometimes you multiply it out. We don't have time to do that, but you could if you want. Okay. And the spectrum is, well, it's the lambdas that give you 0. So 2 and 3. And the multiplicity of 2 is 2 in this case, because you have a 2 minus lambda squared. And the multiplicity of 3 is 1. Any questions on this example? Did I lose you anywhere? By making it triangular, it was a really easy one. If it's not triangular, then that determinant is messy. And factoring, by the way, believe it or not, is the hardest part of the whole thing. Not in this example, but in general, because you're going to have a cubic polynomial. And hopefully you know that cubic polynomials are really hard to factor. Yeah, it's a kernel. So always the kernel. And the kernel is we're setting it equal to 0. And that's why the spectrum is the kernel of the characteristic polynomial. Okay, or the solution setting equal to 0, the roots. Okay, actually the kernel itself are the V's, which we weren't asked for, the eigenvectors. But these are the lambdas that give you a non-trivial kernel.
And we say it's just 2 and 3 for the spectrum because we got 2 twice.
Yeah, because those are the 2 roots.
Yeah, okay.
Right? You get 2, 3, and 2, right? But I said 2 twice, so what you do is you just say the multiplicity of 2 is 2. That means we did 2 twice.
Got it.
And I do want to let you know, remember what I said about chapter 6? What was chapter 6 all about?
Complex numbers.
Right. Why do you think they're going to come now?
Because we have roots.
Yep, you have roots of a polynomial. And roots of a polynomial can give you complex numbers. I didn't do an example of that, but it's not that hard to come up with an example where you get complex numbers for the roots. And that can happen. Okay. And it happens in the real world in a big way. In electrical engineering, it happens in a big way. It happens in a big way in physics. It just happens. I never really understood, like, I know the math, but why are complex numbers like part of the universe? And they are just weird. And I'll just tell you they are, and don't ask me why, but they just come up everywhere. Without complex numbers, we can't understand the universe. Sounds weird?
Yeah, I think about it too, and it's just strange.
Yeah, and you think even more when you understand about this characteristic polynomial coming from the solution to a Schrodinger equation. So just trust me on that. Okay, or electrical engineering. And complex numbers tend to give you the cosines and sines. And that's why you get frequencies and wavelength. Wave comes from cosine sine, and that's because of complex numbers. And remember, e to the I theta is cosine theta plus I sine theta. Has to do with that. So that's all I have to say. So I'm going to stop my share and stop the recording.